This video will look at both confidence intervals and hypothesis tests for matched pair data. Matched pair data happens when you have something that links it together, so some sort of before or after, or if I'm analyzing sample sets for the same individuals. So for example, suppose I want to compare the number of hours that a student spends at the Student Learning Center for different terms. So perhaps I'm comparing fall term and winter term here. Samples 31 students, records the number of hours they attend in both fall and winter term, and gets the following data, and it's the same students for both terms. So even though I collect all of this information, it doesn't mean I should use all of this information. So since it's the same person with the fall and the winter, this feels like it could be linked together. Here's what I mean by that. If a student spends 200 hours in the Learning Center in fall term, they use that Student Learning Center a lot. I wouldn't be surprised if they spend the similar amount in the winter term. If they spend 0 hours in the fall term, they might be more likely to spend 0 hours in winter as well. There's a relationship between the two variables. They're not independent. As such, I don't look at each of the individual terms, but rather I look at the difference of the two terms. In this case, I'm looking at the difference for winter minus fall. I'm going to do a hypothesis test. I always have the same 4 steps for a hypothesis test. First step, I state my hypothesis. My hypothesis, in this case, average is equal to 0. Now notice what I've done here. I have a single average because I'm looking at a single list of values, and that list of values is the difference. So test if there's a difference. If I'm testing for a difference, that's a not equal to kind of situation. Model. Well, I have the model that I would have if I was working with a single average. That model again is x bar follows a t-distribution with degrees of freedom n-1, with an average of mu coming from the null hypothesis and a standard deviation of s over the square root of n. In this case, since I'm working with differences instead of just any old list, this has a little bit of special notation. But you should keep in mind that this is really just the same setup that I had previously when I was looking at one list of statistic stuff. So d bar instead of x bar, I'm being specific, I'm looking at average of the differences, mu of the difference, and just like when I've compared every other group thus far, that average has been 0. Standard deviation for the difference, and here I have k representing the number of groups. So for example, for our set, d bar will have a t-distribution. I was looking at 31 students. So k equals 31 students gives me 30 for my degree of freedom. I have a center of 0 and a standard deviation of 2.4 over the square root of 31. That center of 0 comes from the null hypothesis. This is claiming that there is no difference. Now looking at the data above, I see that the actual difference for the sample was -6 hours, but I don't know what that means about the overall population. That's what I'm ultimately testing here. Because maybe I just found an odd sample. Okay, so I'm expecting a difference of 0, give or take 0.431 or so. P-value, I am testing any difference. My sample average was -6, or more extreme, I'm testing for values different than that. I'm going to draw just a sketch of what's going on here. The center I'm expecting to be 0. I'm counting by about 0.43 or so. And the value that I detected for a difference was -6. Oh, dang. -6 is going to be way, way out there. This is a two-tailed test, so I'm going to shade both the left tail and the right tail I'm going to have a really, really small p-value. This is going to be a 0 plus kind of situation. Let's find that t-score, and I do so by taking my value, -6, minus my center, 0, and I divide this by the standard deviation. This is the same way I find z-scores as well. I do value minus center over standard deviation. When I type this into my calculator, I end up getting a t-score of -13.92. That's a ridiculously small t-score. I can look this up using technology. So I'm going to do 2 times because this is a two-tailed test, TCDF. If I'm looking at this left tail starts at -infinity. It goes all the way up to -13.92. And my degree of freedom was 30. I can look this up doing second vars if I'm working in a TI-84. If I'm in an 89, I can go apps, stat list editor, and then up at the top, I can choose the option for distributions. Or I can do this inside of GeoGebra by going into probability and then choosing the student distribution. I'm going to use my TI-84 TCDF -infinity to -13.92. My degree of freedom is 30. 0, so small it thinks it's 0. I'm going to multiply this by 2 just because I know I'm supposed to. I still get 0. So my p-value is 0 plus. It's not actually 0. There's still a little bit of area, but it's so small that my calculator can't even detect it. Conclusion, if my p-value is low, and let's say we're using an alpha level of 5%, if my p-value is low, the null must go. So p-value is less than alpha. I will reject the null hypothesis. I have evidence that students use the SLC differently in fall versus winter term on average. But this doesn't tell me which term they use the Student Learning Center more, and it doesn't tell me how much more. If I'm asking a question of how much, that's a confidence interval question. If I'm just asking, does there appear to be a difference, that's a hypothesis test question. In general, hypothesis tests end up being some sort of yes or no thing, and a confidence interval ends up being a range of values. So my confidence interval formula, I'm working with a single average, so I'm going back to my old one of x bar plus or minus t star, whatever my degree of freedom is, s over the square root of n. I'm going to write this with the notation for what it looks like when I'm working with matched pairs. So this would become a d bar plus or minus t star. It's the standard deviation of the differences, and it's k for the number of groups, but it's still working exactly the same way. My sample difference on average was -6. I'll circle back to this t star critical value thing. My standard deviation was 2.4 over the square root of my k is 31. I actually know what the standard deviation is. I did it over here. This is 0.431. So I really just need this t star for 30 degrees of freedom. And let's create a 95% confidence interval here. So I'm going to go to my t table, and I'm going to see where the 30 row meets the 95%. So here I have a t table, 30 as my degree of freedom. I want to find where that 30 meets my 95 and appears to do so here at this number 2.042. So my critical value is 2.042 or so. I'm going to multiply that 2.042 times that 0.431 to see how much I'm adding and subtracting. That number is called the margin of error. So my mho is 0.880 or so. So I'm going to do this once with the minus and once with the plus. With the minus, I get negative 6.880. My units here are hours. With the plus, I get negative 5.12. The units again are hours. Now, obviously, you can't study a negative number of hours. It's not like you're so bad at studying that you distract your neighbors from studying. That's not what this means. This is the difference between the two groups. In particular, if I have a negative negative or a positive positive, this tells me that there is a difference on average. If I had a negative positive situation where I had 0 inside of my interval, this would give me inconclusive results. So I do the analysis just like I would for one sample average, but I do the conclusion like I would if I'm comparing two groups, because I am comparing two things. So in this case, my average for the difference, and the difference was winter minus fall, was a negative number. So this told me that my winter minus fall number was less than 0. Moving this f to the other side, this told me that students were spending less time on average in winter term than they were in fall term. So I am 95% confident that students on average spent more time in the fall than the winter by, and if you're wondering by how much, well, that's what these numbers tell me, by anywhere from 5.12 all the way up to 6.88 units here, hours. So not only do I have evidence of a difference, the confidence interval is way more descriptive. It tells me what that difference is. I am 95% confident that on average, students spend more time in fall term than winter term, anywhere from 5.12 to 6.88. That's a substantial difference between those groups. That's why I'm seeing me reject this null hypothesis and having this t-score of negative 13. That's ridiculously large. That's off the table, is kind of rare. That gave me a p-value of 0 plus. So inference for matched pairs, this might seem like it's new material, but it's not. It's really just doing the inference for a single average, but thinking in the conclusion, I'm comparing groups.